All right, here we're going to continue our discussion of excess properties, now looking at the case of entropy and molar Gibbs free energy. And just a little recap of the last set of notes. Remember, if I'm thinking about F being some arbitrary thermodynamic state function, and then our definition of an excess property, right? So Fe is actual relative to that of an ideal solution at the same conditions. Okay. And likewise, we saw that partial molar F of component I is equal to actual relative to that of an ideal solution at the same conditions. All right, so excess is actual relative to that of an ideal solution. So something will pop out when we look at entropy and molar Gibbs free energy. So spoiler alert, but just to make you aware, so that when we see it, we'll draw attention to it, is another representation that we'll see in this set of notes is that an excess property is likewise equivalent to delta F of mixing, so my actual property change upon mixing, relative to that of an ideal solution, right, at the same conditions. Okay, so my excess property, right, is actually excess property change upon mixing, right? So essentially, what you might think of as your excess property change upon mixing, right, is just my excess property. So it's property change upon mixing relative to that of an ideal solution. Okay, so let's pick up with S. Okay, so my excess entropy, okay, SE, would be equal to my actual entropy relative to that of an ideal solution. Okay, so as taken aside here, okay, remember that S ideal was equal to, term to remember, it's sum over I, xi log xi. Okay, I'm thinking about property change upon mixing. Okay, so let's take this as two steps. Okay, since I'm doing it, all right, so delta S of mixing, okay, remember of ideal solution, term to remember is sum over I, xi log xi. Okay, delta S of mixing is always going to be positive, log xi is always going to be negative, so this could be a negative R, right? Negative to make it positive, R gives me my units of entropy. So S ideal then, right, it's just sum over I, xi si, plus delta S of mixing of an ideal solution, right? Which in this case is just this minus R sum over I log xi. So if I come back here then, right, for SE, okay, SE is S, so it's a minus, so it'd be a minus sum over I, xi, si, minus delta S of mixing ideal, right, which would be a plus R sum over I, xi, log xi. Okay, and so this is where, before we even proceed, okay, this S, my actual S relative to that of the molar average of the pure component systems I mix at the same temperature and pressure, okay, this is our definition of delta S of mixing. Okay, as we just saw here, right, this is negative delta S of mixing of my ideal solution. Okay, and that's where we get that in general, my excess property is also equivalent to property change upon mixing for my actual system relative to that of an ideal solution, right? Cool. So SE I can see is delta S of mixing minus delta S of mixing ideal. This wasn't apparent when we looked at enthalpy, internal energy, molar volume, because, well, delta H of mixing for an ideal solution is just 0, right? And so 0 is invisible. You can't see it, right? So we could have said it, but it wouldn't have made much sense. You could have said, hey, you could just be making that up. Okay, so all right, so if I continue on, okay, SE again, okay, is going to be equal to S minus sum over I, xi, si plus R sum over I, xi log xi. Okay, so here's my expression for SE. Okay, next, if we wanted to get expressions for our partial molar entropy, we could go two routes. Okay, we're going to go both routes in the interest of trying to get you to learn said concepts. Okay, but route one, which I Well, let's do the matching route. Let's do, route 1 in this case will make the more tedious route. Okay, and so what I mean by that is I'm going to take S, okay, and S I can write as being equivalent to the molar average of my partial molar S's in my solution of interest. So it'd be a minus sum over I, xi, si. And while I'm at it, just like if you think back to our ideal solution notes, and we do kind of these matching exercises to get expressions for my partial molar properties, I'm going to bring R into my sum. Okay, so I'm going to bring R in my sum here, and I'm going to rewrite this as plus sum over I xi times R log xi. Okay, now that must be equivalent to, okay, so I know that we said S is equivalent to molar average of my partial molar S's. Okay, likewise, SE would be equal to molar average of my partial molar SEs. Okay, so all of our expressions that we've worked out in chapter 5, differential expressions are applicable to residual properties. They're applicable to excess properties. They're applicable to partial molar properties. All of our equations, right, are equally valid for all these cases. So I'm going to write this as sum over I xi s bar I e. Okay. So if you look at the left-hand side, okay, the last step of this is to collect terms. So this could be sum over I xi times s bar I minus, okay, it's a minus si plus r log xi. Okay, and that has to be equal to sum over I xi s bar ie. So for these two expressions to be equivalent, it must be then the s bar ie is equal to s bar I minus si plus r log xi. Okay, so that's route 1. Route 2 is, remember, s bar ie is equal to s bar I minus s bar I ideal. Okay, so the key is trying to remember, what is s bar I of an ideal solution. Okay, well, we showed in the last, 2 sets of notes ago, our review from chapter 11, that would be equal to si minus r log xi. Okay, and so remember, key is this log xi term. Xi will log xi is going to be negative since xi is going to be less than 1. So the negative sign makes that positive. Right, my partial molar property is greater than, in the mixture, is greater than the pure component molar value. Okay, so this is equivalent to just saying that my partial molar excess property is equal to my actual partial molar property relative to that of an ideal solution. Right, you would end up with the same expression. Right, so it's entirely up to you how you go about it. Now, if we think about G is actually going to give us 3 options. So we could tackle G in a number of ways. Okay, let's option 1, right? So if I want GE, okay, I know that G is defined as H minus TS. So G I could write as being HE minus T SE. Okay, cool. So therefore GE, okay, must be equal to, okay, what was HE equal to? Do you remember? Actually, it's tough for me to remember too. But remember, okay, HE is going to be equal to actual relative to that of an ideal solution. So that would be H minus sum over I xi hi, right? Would be one way to write it. Okay, and so if I were to go that route, this would be H minus sum over I xi hi minus T times SE, right? SE we have here, right? SE would be, let's get my stylus, S minus sum over I xi si plus r sum over I xi log xi. Okay, cool. So if I expand, then I have that GE is equal to H minus sum over I xi hi minus TS plus T times sum over I xi si minus RT sum over I xi log xi. Okay. All right. So now let's collect terms. So GE, okay, would be equal to, okay, first I'm going to group these two terms together. Okay. So it'll be H minus TS. Then next, I'm going to group these two terms. Okay. And we'll take this in steps. Okay. But if I was just to group terms initially, let's write this as plus, and then I'm going to write minus sum over I xi hi plus T sum over I xi si minus RT sum over I xi log xi. Okay, so this first term, GE, okay, H minus TS, that's just my definition of G. Okay, here what I'm going to do is, so we're mixing at constant temperature and pressure, right? Everything's at constant T and P. It's actual relative to that of an ideal solution at the same conditions, right? The same T and P. So T is going to be constant, and I'm going to bring it in my sum. And so I'm going to write this as minus sum over I xi hi plus sum over I xi t si minus RT sum over I xi log xi. Okay, cool. So I have GE is equal to G. Okay, here, all right, if I collect terms, write that as plus. Now I'm going to have, ideally could have made it minus, but doesn't matter. I'm going to write this as sum over I xi. Then this will become, and we can keep the negative. Let's keep the negative in front there. Hi, so it's got a negative out here, minus T si minus RT sum over I xi log xi. Okay, Hi minus TSI, that's just GI. So we get that GE is equal to G minus sum over I xi GI minus RT sum over I xi log xi. All right, cool. Route 1. Okay. Route 2 would be, well, we just showed that GE I could write as being equal to delta G of mixing relative to that of an ideal solution. Okay. Well, that would tell me then that GE is equal to G minus sum over I xi GI. Then it's a minus delta G of mixing of an ideal solution. So that'd be a minus RT sum over I xi log xi. Okay, which is equivalent. Okay, cool. And if you wanted to do option 3, right? Option 3 would be, we could write this as GE is G minus G ideal, right? Where this is negative G ideal, right? So I won't bother to do it because you're just going to get the same equivalent expression, right? Then there's just as just as many options to calculate my partial molar properties. So namely, did we get partial molar S? Yeah, we did partial molar S, right? So one option would be my partial molar XSG. Okay, which I'll point out is equivalent to my excess chemical potential, would be equal to actual relative to that of an ideal solution. Okay. Well, that would be what? G bar I. Oh, now I have to jog my memory in terms of this is a plus or minus. Sign would be opposite of S. S is minus R log xi. So it should be G bar I plus RT log xi. Okay. And again, this is equivalently, chemical potential. So this you could write as mu I. Okay. Right. So that'd be, one way. Another way would be G bar I excess. So G is H minus T S. And so that would give you HI minus T. And then S bar I excess was S bar I minus R log xi. Okay, so you'd get that G bar I excess is equal to HI. Hold on, what am I? Oh, H bar IE, okay, is actual relative to that of an ideal solution, so it's H bar I minus HI. That's minus T S bar I. Oh, hold on. Now I've got to, please pardon me, allow me to redo this one just to make sure I'm not goofing up. So H bar IE, right, would be, so in an ideal solution, my partial molar enthalpy is just my pure component value. Okay, so that's where I have H bar I minus HI. Now S bar IE, okay, so we work that out up here. S bar IE is S bar I minus SI plus R log XI. Okay, so my apologies, I was looking at the wrong thing. And actually, you're going to have to allow me, so pardon me as I rewind, because we're going to have to do both of these over again. Okay. So you get to see me in live action, just like this were class. Okay. So looking at here, right? So G bar IE, okay. All right. This is actual relative to that of an ideal solution. So it's G bar I, okay. Then minus, okay. What was G bar I ideal? Okay. So if you were to look back at our notes, G bar I ideal should be GI, and then it's always a matter of remembering if it's plus or minus. Okay, and so this is where I'm going to peek back at entropy. Where do we write down SI ideal? Right, S bar I ideal was SI minus R log XI. So G is going to have the opposite sign. Okay, and it'll be plus RT log XI. Okay, and so to help me remember this, right, this is supposed to be G bar I ideal. Okay, and so G bar I ideal, the effective molar Gibbs free energy in my ideal solution is going to be less than that of my pure component value, because this term will be negative. Okay, so that would tell me then that G bar IE is equal to G bar I minus GI minus RT log XI. Okay, and again, you could replace this with chemical potential if you so choose. Okay, which also brings us to, you could get this same result by looking at definitions of fugacity, playing with fugacities. Okay, but that'll come about later. The other way we had just said is G bar IE would be H bar IE minus T S bar IE. Okay, H bar IE. Okay, so that would be my actual partial molar enthalpy relative to that of an ideal solution. Well, in an ideal solution, it's just HI. Okay, then it's minus T. S bar IE is actual, okay, relative to that of an ideal solution. All right, in an ideal solution, we have SI minus R log XI. So minus SI plus R log XI, since the signs are going to change. So if I expand, I have H bar I minus HI minus T S bar I minus T SI minus RT log XI. So H bar I minus T S bar I is G bar I. This is minus minus, this should have been plus. Okay, this, so again, H minus TS gives me G, so this is a negative GI, and we get that G bar IE is equal to G bar I minus GI minus RT log XI. Right, so we get the same expression that way. And you could equivalently play with your excess property, the match terms, right? But it's all the same. Okay, cool. The last thing I'd want to point out is, let's see if we can get it from any of our expressions here. So let's look at, say, this expression, right? So excess property is actual relative to that of an ideal solution. An ideal solution is a system in which all of our intermolecular interactions are exactly the same. Okay, so in a pure component system, right, if we have a system of pure component 1, all of our interactions are exactly the same. So a pure component system is an ideal solution. So therefore, in the pure component limit, all of our excess properties should be equal to 0. Because if in the pure component limit I'm by definition an ideal solution, then my excess property should be 0 in that limit. And so if I look at, say, this expression for GE is G minus sum over I xi GI minus RT sum over I xi log xi, you should recover exactly that. So if you, so you would recover exactly that. Your excess property is going to be 0 in the pure component limit. So mainly, let's see. So if you had let's write it down for a binary mixture. And maybe it'd be even easier if we were to look at enthalpy, then we wouldn't have to worry about these log terms. Okay, but if I were to look at, say, enthalpy, HE is actual relative to that of an ideal solution. All right, so that'd be H minus sum over I xi HI, or equivalently, this is sum over I xi H bar I minus HI. All right, since H is just molar average of my partial molar values, right? And so, now it becomes obvious, right, in pure component limit, my partial molar property is just equal to my pure component molar value, right? So this term here, right, goes to 0. So in the pure component limit, your excess property is 0, because in the pure component limit, I have an ideal solution. Okay, and again, all of the expressions that we've worked out previously, all of our differential expressions are just as applicable to excess properties as they are to residuals or anything else. So the one I'll just mention now, because it'll come up later, right? So the Gibbs-Duhem equation. So remember, that was our 0 sum requirement. So sum over I xi d f bar I is equal to 0, right? And so we're going to get an equivalent expression with partial molar properties. Okay, and with that, we'll stop this set of notes.